Okay, greetings everybody. We're back with Stat Inference. I'm gonna compress 2 lectures into 1 lecture. So this might take roughly an hour, hour and a half, somewhere in there. So I'll try to save a little bit of time. We're gonna pick up with minimal sufficient statistics. We had a definition that we had learned in the previous lecture that this says it is a function of all other sufficient stats. Now that's not a very useful definition. I think it's accurate. We saw an example last time. I'll just walk us through that example one more time, discuss this, then I'll show you the tool that we use to verify things are minimal sufficient. But keep in mind, what I really do is I use the factorization theorem to recognize sufficient stats, and then I mentally think about all my arithmetic tools on how to compress things down. So if I have a big sum, I don't need all of the elements. All I need to do is compute that sum. And I can forget about what the actual individual elements were. And we've seen examples like that. We'll see that example right here. So the example that we studied in class was XI, was Poisson, IID stuff, and we'll call the parameter theta. We'll see n of these data points, and we'll see what's sufficient. Of course, all the data set is sufficient. So the data you get is probably the highest dimensional form that you can do your inference with, but this is sufficient. In IID problems, we've already learned that IID problems are exchangeable problems, so the order doesn't matter in IID problems. So this is also sufficient. So I'll say X ordered the order statistics are also sufficient, where these things are all less than or equal to each other by the definition of what an order statistic is. I can rearrange them in any way, and I still have the same information about everything. And that's just because products, I can move them around. So I can commute. So our joint distribution is just going to be the product. I goes from 1 to n, e to the minus theta, theta to the xi over the xi factorials. So I can rewrite this thing down. I should probably tell us that the parameter is positive, so I like to always do this, not just tell you the functional form, but tell you the restrictions. So this is going to be e to the minus n theta, theta xi over xi factorial. I got to bring my product in, so I'm going to bring that in to the sum. I goes from 1 to n, and I still have a product down here. And you're not going to be able to simplify that any further. The good news is that it doesn't tell you anything about theta. So this part of everything, at least in the way we're thinking about this, all the information is up here. So when I'm trying to ascertain what theta is. The likelihood function is sitting right here if I think about this as a function over theta. So there's some curvature to this right here. And regardless of how I write this down, I could have written it down this way, or I could write it down this way. So when I'm writing it down in the full product form, then I need to know all of the xi's. If I simplify everything, all I need to know is the sum of the xi's. And then for the asymptotics, we'll need to know n as well. So I still have some action going on here, That's just pushing things down harder and harder as n gets bigger and bigger and bigger. What that really relates to is my likelihood is getting peakier and peakier because of that. But this is sufficient as well. So I could use the factorization theorem and write out what all this stuff is. So I might write down that g tx given theta is going to be equal to e to the minus n theta, theta to the sum of the xi's. And in the factorization theorem, there's this other part, h of x. And for our case, this would be 1 over the product of the xi factorials. So we can factorize everything and recognize that I do have a sufficient statistic right here. I'm also doing the mental factorization where I'm compressing this. So you give me the likelihood of a function, and so long as it's reasonably simple and I can get my head around all the little parts, I can probably recognize what the minimal sufficient stat is by using the factorization theorem and then doing the compression. So this right here is one-dimensional. And of course, these things right here, this is n-dimensional. That one, and this is also n-dimensional. So in terms of the dimensionality of everything, this one is smaller. Now theta is one-dimensional. Sum of the xi's is one-dimensional. And so you're never going to have a zero-dimensional stat or a 0.5-dimensional stat. So that doesn't exist. So we live in this restricted world where we can either hold it or we can't. So one-dimensional thing for one-dimensional parameter, that's the minimal sized statistic in terms of dimensionality. There's a lot of stats that we could write down. So we could write down sufficient stats that look like this. xi, I'm going to say I goes from 1 to some number k. K is going to be less than or equal to n. I'll say it's less than strictly. Actually, I'll say we'll do this a couple different ways. So I'll introduce a k prime. I'll say that I have a sum, and that k prime is going to be less than n. I goes from 1 to k prime plus 1. And I'll say this goes to whatever I want to make this. I'll say that this is k double prime, which is less than n. And then I'm going to introduce a new one, and I'll say that this goes from I goes from 1 to k double prime to n, xi. So this is also a sufficient statistic. If I add these three things together, I will get that. So this is three-dimensional. So I've got a whole bunch of sufficient stats. I can compute from this, I could compute that sufficient stat. Or I could take this n-dimensional thing and I could compute that sufficient stat. I could use this to compute that sufficient stat. But I can't go the other way around. From this, I can't recreate what those are. From this, I can't recreate what that is. From this, I can't recreate that. So this sufficient stat is a function of all those other sufficient stats and any other one that you could write down. And that's where this definition comes from. So a minimal sufficient stat is one that I can compute from any other sufficient stats. Can't go the other way around. So slightly elusive definition at first, but I think it makes sense. What we really just need to know is the xi's, or the sum of the xi's for this problem. You've got to tell me n as well. Usually we're given it. Okay, so let's write down what the book says for a minimal sufficient stat. So this is a more usable definition. So minimal sufficient stats. So here's our definition. If I take F of X given theta, so I'm just thinking about an arbitrary distribution, theta is arbitrary, X is arbitrary in joint form, and F is arbitrary. So if I look at this, and I divide by this thing right here, Fy given theta, this should be a constant, and there's this condition. If and only if Tx is equal to Ty. That's what they present to you in the book, and they say that this is going to be minimal sufficient if this is satisfied. So if this is a constant right here, then we would say that T is sufficient. And the only if part is the minimal sufficiency part. So what we've really done in the first direction is checking to see if this is a constant. This satisfies our original definition of sufficiency. That I'm taking these two ratios, I'm dividing them by each other, and it's constant with respect to theta. That's telling us that it's sufficient. It's this other direction that if this is equal to that this will be a constant is the minimal constraint. Let's think about that in terms of this Poisson problem. So let's just think about an example. Try to apply this definition. So back to our example. Xi's are Poisson, theta, and I'm going to think about Yi's being Poisson theta as well. This will be I goes from 1 to n. And same thing over here. Both of these are IID. So let's just form this ratio. F of x given theta divided by Fy given theta. I'll just write this down in terms of its product form. E to the minus theta, theta to the xi's. I goes from 1 to n, e to the minus theta. Oh, and I need to write down my xi factorial right there. I'll finish the denominator, theta to the yi's divided by yi factorial. And I want to think about when this thing is a constant. So basically, when do these things cancel each other out? This one already cancels, right there. So it's not doing anything for us. So this will be a constant under a lot of different conditions. So it's a constant if, and I'll give you one such condition when this thing is a constant. It's a constant when all of the xi's are equal to the yi's. So if the xi's are equal to each other, everything is constant. For I goes from 1 to n. So of course they will be, because all of these little terms will be the same. It's also a constant if this is true. So I don't actually need the xi's to be the yi's, and I'm pre-assuming that there's some order. If I sampled n times from some Poisson distribution, be extraordinarily unlikely for this to happen, for that to occur, where they're all exactly the same. We don't actually need that. We could have this being the case. If the order stats are equal to each other, for I is equal to 1 to n. So we could have that, and that ratio will be a constant because I can shuffle the order of my product and it's still the same product. So everything commutes. I don't need for this to be true. But what I'm noticing, if this stuff is true, then this ratio right here would be a constant. And so that's the if direction of everything. What we're really doing on that if direction is checking sufficiency. So in this one direction, if this thing is a constant, then we've checked sufficiency. So this is telling us about sufficiency. This part, the only if, is going to tell us about minimality. Min sufficiency. So this is the restriction. So only if this is true. And so I don't need that to be true. There's something else that I necessarily need to have for everything to be min sufficient. So this will reduce to, I'll get rid of these, and I'll just have theta sum of the xi's, I equals 1 to n over theta sum of the yi's. I goes from 1 to n. And I guess I can write it down like this. So this is going to be the product. Yeah, I'll flip them upside down. Lots of ways to write the exact same thing. So these are in each other's denominators, so they just flip over. And so this thing is already a constant. That's a constant no matter what I do. It has no thetas in there, so I don't have to worry about this. This isn't going to affect the constancy of that ratio. I just need to think about this thing. And so really the necessary condition for this is that the sum of the xi's is equal to the sum of the yi's. So sum of the xi's is equal to the sum of the yi's will also lead to a constant. I goes from 1 to n, I goes from 1 to n. And so this is the necessary condition. This is the necessary constraint for it to be a constant. And that's what they're talking about right here. So the first part tells you it's sufficient. In the second part, adhering to this constraint, that it's only a constant if that is true. This is the most binding constraint that you can come up with. So that's the necessary condition, and that's what's telling us that it's min sufficient. Basically, we're just thinking in a lot of different ways, how do we prove that we can't go any smaller with anything? If this definition works for us. So that's what a minimal sufficient statistic is. Let's look at one more example. So let's look at a Cauchy distribution. So one more example. Xi's are coming from a Cauchy. And I'll say my Cauchy has location parameter mu and scale parameter sigma. Again, everything's IID. And I'll have n draws right here. We'll do the same thing. Think about some hypothetical y's. We'll let them be Cauchy as well. Mu sigma. Again, I goes from 1 to n. So I know what Cauchys look like. F of x given mu and sigma. Let's say this is theta. F of y given mu and sigma. Again, we're calling that theta. And it actually doesn't matter. Theta could have just been mu and sigma given, or you try to infer sigma. So the same thing's going to happen in all of these cases. This is going to look like product over some product. Normalizing constants are going to cancel, so I don't even need to write them down. This is going to look like this. 1 over sigma, 1 plus x minus mu squared. This is going to be sigma squared right here, and this is raised to the minus 1. So if I were dealing with a t-distribution, same sort of thing. I would have a nu right there, and this would be a nu plus 1 over 2. So the same thing happens with t-distributions. This is xi's. This is going to be my yi's. Yi's minus mu squared over sigma squared, raised to the minus 1. So this part cancels. We don't need to even think about that. I just thought I would write it down since it's one of our parameters of interest. So I don't cancel parameters of interest like I do normalizing constants. I write them down and then I cancel them. But normalizing constants I always just throw away. So when I'm doing problems. Okay. So the question is can I simplify all of this? So this is just going to be equal to, I'll just make this a little bit more obvious, x1 minus mu squared over sigma squared. 1, so I'll just say dot, 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 give myself a little bit of room. 1 plus xn minus mu squared over sigma squared. This is raised to the minus 1 there. So multiplication. And something similar over here, 1 plus y1 minus mu squared sigma squared to the minus 1 times dot, 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 all the way out here. And this is raised to the minus 1 power. So you can try to simplify this form until you're blue in the face, but you're never going to. So I guess if we were number theorists, we would show that there's no reduction to this polynomial. So in terms of mu and x's, right here I've got the squaring coming in, then I have a product over n of those things, so I have a polynomial of size n times 2. And I can't reduce that. I always have that big polynomial. So a lot of powers are soaking up right here. So they're all going to include all these little terms. So I'm going to have all of the 2n terms, the 2n minus 1 terms, I'm going to have the 2n minus 2 terms, all the way down to the constant term in here, the intercept in that polynomial. So there's no reduction. Now I don't actually need the xi's and the yi's to be equal to each other. So I can come up with something a little bit more unconstrained, but it doesn't help in terms of the minimal sufficiency. So we could have, for this ratio to be a constant, all the xi's to be equal to yi's. Then this thing right here is equal to a constant with respect to theta. Or I could even have maybe the order statistic. Maybe that's a little less binding. Xi, yi is ordered. That's going to lead to this being a constant. So the xi's, all the collection of x1 through xn, that's n-dimensional. So this goes from I goes from 1 to n. I goes from 1 to n. So this thing right here is n-dimensional. This is n-dimensional. So it might be a little bit more polite to say the order doesn't matter in all of this, but as soon as you said the problem was IID, you've already said that, and we've proved that if things are independent, they're exchangeable, not the other way around. So this is an n-dimensional sufficient statistic. From this, I could compute that if you would like. So from this, I can't necessarily compute that and say how they came at me. So this is the polite way of saying things are minimal sufficient. So x1, x2 ordered all the way to xn. Is minimal sufficient. So no reduction in there. We can think of a lot of problems where there are reductions, and we can think of a lot of problems where there's not reductions. Here's a fact, and you get to play around with this on your homework. Exponential families always have a reduction. And that's kind of nice. So if you're playing on a computer with exponential families, you can speed up your code. Or you can save some space, save some RAM. And so exponential families have some important implications, that there's always a nice reduction, and in some sense that's a lot more important than just a mathematical peculiarity. It's useful to us. If you're working with Cauchy distributions or T distributions, there's no reduction, so your code is always going to take a lot more computation to work with. The good news is there's ways to parallelize that code so that you can play around with Cauchy distributions and T distributions and do it at practically, at least in terms of human time. If you parallelize things well, you can do everything very fast. So there's computational tricks to get around the no reduction, but we need parallel processors. Good thing at universities, those are free to us. So we have places like advanced research computing where they'll give us as many cores that we really need. Of course, there is a limit, but for all intents and purposes, there's no real practical limit here. So no reduction there. And there's lots of problems like that. So I'm just going to leave it at that. That's what minimal sufficient stats are. And I'm going to go into ancillary statistics next. I think I've saved some time on this. We did that pretty quickly. I'm going to cut this video out just to partition everything nicely. And I will come back in just a moment, and I'll be talking about ancillary stats. Thanks, you guys.